All right, we're going to finish up with our last topic of the year. We didn't get through everything, obviously, but kind of hit some highlights, and that's what we're going to do today, talking about titrations. Acid rain, talk about that for a minute. There's a lot of industrial processes that produces gases like nitrogen monoxide, dioxide, carbon dioxide. So you may have a plant, please ignore my drawing, that's producing all these gases, CO2, SO2, and then it rains. So that gives me some H2O. So then those things combine and we end up getting our different acids. So something like carbonic acid, or maybe sulfuric acid, or sulfurous acid. But these are acids, remember, because they start with hydrogen. Then those come down and they hit buildings, and they can cause some things to decompose, especially things made out of calcium carbonate, which are going to be sold at some of our older buildings, some of our older statue structures, and can cause a great deal of damage. So when people talk about acid rain, that's what we're talking about. It's not that acid is actually being rained onto things, but the water from the rain is combining with some of these gases, and then we end up with our different acids that can actually cause a problem. All right, so let's move on to titrations, because that's what we're going to spend our time doing today. Neutralization reaction is a type of double replacement reaction. We've talked about that before. So a neutralization reaction is the reaction when you have an acid and a base and they produce water and a salt. And remember, in chemistry, a salt does not have to be sodium chloride. A salt in chemistry is any ionic compound, metal plus nonmetal. So you're going to get the cation, your positive cation from the base, and your negative anion from the acid. And that's where you're going to end up getting your salt. So a neutralization reaction occurs when you have the same number of hydronium and hydroxide ions. As we talk about titrations today, we're going to be talking about strong acids and strong bases when we mix those two. So if I have a strong acid plus a strong base, that's going to give me the neutralization reaction. And when I get to the end point, the pH would be about 7. Now, if you take AP chemistry, or when you move to chemistry in college, you're going to see that if you're mixing, let's say, a strong acid with a weak base, when you get to the end point, it's not going to be at a pH at 7. So we're taking what the easiest route is. Strong acid, strong base calculations are easy. If you start throwing in some weak acids or weak bases, then it gets a lot more difficult, and that is something that you'll handle at a higher level. So if we look here, and every time you see these little boxes, those are supposed to be arrows. I don't know. Whenever I take it from the notes to Google Docs, that's what happens. So hydrochloric acid, my strong acid. Sodium hydroxide, my strong base. Remember, I know it's a hydroxide. I know it's a base because it has the hydroxide group. So the hydrogen from the acid combines with the hydroxide from the base, and that's where I get my water. That's what this is, HOH, just a different way to write it. And then what's left over, my cation from my base, my anion from my acid comes together to give me a salt. And in this case, it happens to actually be table salt. Remember, you always write your cation first and your anion second. Now, these types of reactions are written as net ionic equations. I'm going to mention it. We're not going to spend time like we would if we haven't gone through all of our COVID things. But if we go all the way back to double replacement reactions, when we used our solubility rules, we know that if we put a strong acid like hydrochloric acid into water, it's going to ionize completely or break into its ions. Sodium hydroxide, a strong base, by definition, is also going to ionize 100% or break into its ions 100%. H2O is a liquid, so it's going to stay together. And then sodium chloride, right here, my sodium chloride, has a group 1 metal, and by our solubility rules, all group 1 metals always ionize completely in aqueous solution. So that's why it's written as ions. So if I look at that reaction, if I have one thing on the reactant side and the same thing on the product side, it can cancel. So that's why my sodium can cancel and my chloride can cancel. And so this is called my net ionic reaction. It is a reaction that shows, or the equation that shows, what actually reacts or changes. So really the only thing that changes in this reaction is my hydrogen ion combines with my hydroxide ion to give me some water. Sodium and chloride are called spectator ions because they are not really part of the reaction. They don't change. They start off as ions, they end up as ions. So that's what just a quick what a net ionic is. All right, but really what we're going to spend time today on as titrations and the calculations that involved a titration. So when you're dealing with a titration, the reason that we even carry out a titration is that we're trying to find an unknown concentration of a compound. And that most often is we're trying to find the molarity of some unknown compound. So I have a known and I know its strength, and then I have an unknown and I don't know its strength. So that's the whole reason that a titration is carried out. So for acids and bases, titrations are neutralization reactions of an acid plus a base or vice versa. It is usually used to find the concentration and molarity of an unknown acid or an unknown base. The concentration of the other is known. So you would have to either know the strength of your acid and be trying to figure out your base, or you would have to know the strength of your base and be trying to figure out your acid. The titrant is a solution of known concentration, and it's in the burette. The titrant is added to the solution of unknown concentration until the substance being analyzed is just consumed. And we say this is the stoichiometric point, or usually it's referred to as the equivalence point. So we titrate until we hit the equivalence point, because when we hit the equivalence point, we would be able to carry out calculations to figure out what the unknown is. To figure out that we are at the equivalence point, we look for the end point. And the end point is a change in color that is seen whenever the titration is over, or whenever the titration has hit the equivalence point. So examples of that would be phenolphthalein and methyl orange. Phenolphthalein and methyl orange are indicators. This is supposed to be an or. If I can change it, let's see. So phenolphthalein and methyl orange, both of those are indicators. So they're going to be one color when the pH is basic, and then they're going to be a different color whenever the pH is acidic. So you look for that color change, and that tells you that the titration is over or that you've reached your equivalence point and the titration should stop. And then you would make all of your measurements and be able to carry out your calculations. By definition, the equivalence point is a point at which the two solutions used in the titration are present in chemically equivalent amounts. So if we're doing an acid and a base, this is going to be the equivalence points. Is going to be whenever your moles of hydrogen ions is equal to your moles of hydroxide ions. And if you have picked your indicator correctly, when this happens, when we're at the chemically equivalent amount equivalence point, then you should see a color change, and that's what indicates that the titration is over. In Chemistry 1, you would be told what indicators to use, and probably the most common one for us is we would be using phenolphthalein. In college chemistry and in AP chemistry, you have to sometimes make some decisions on what indicator to use based on whenever the equivalence points would be met. If you've figured out or if you've chosen your correct indicator, the equivalence point and the end point should be equal to each other. Sometimes they're not exactly to each other, but they should be very close. For a strong acid and a strong base titration, where we have that simple net ionic reaction that we looked at, where a hydrogen ion and a hydroxide ion, the hydrogen from the acid, the hydroxide from the base, come together to form water. The pH is easy to calculate because the reactions all go to completion, and the equivalence point is whenever my pH is going to be equal to 7. Like I said, this is just strong acid, strong base. All right, so that's what we're going to be looking at today, strong acid, strong base titrations. So if you watched the video that showed the titration, these words that we talked about today should sound familiar to you. Titrant and burette, that would have been seen when you watched the video. Another word that was mentioned in the video was analyte, A-N-A-L-Y-T-E, analyte, and that would be the one that you, that would be your known solution, or the solution that you know the concentration of. I'm sorry, your unknown solution. Unknown solution, not your known. Because your your known solution is going to be the one that's in your burette, which is going to be your long, thin tube that has all of your good demarcations on it. All right, so let's look at the formula. It's really easy to use. It's going to look very similar to a formula that we have already used. Thing that's going to make these a little tricky is that you have to be able to write your formulas for your acids, which sometimes we forget how to do that. All right, let me move this up a little bit. All right, so the formula that we use is MAVANA and then MBVBNB. So obviously the A and the B, that stands for acid or base. So MA and MB is going to be the molarity, big M, of acid or base. Remember, your acid's going to start with a hydrogen. Your base is going to have a hydroxide. VA and VB is going to be the volume of the acid or base. It can be in milliliters or liters. It just has to be the same. So in other words, if the volume of your acid is in milliliters, then the volume of your base would be in milliliters. Na is going to be the number of moles of acidic hydrogen, which sounds pretty complicated, but in the formula, it's just going to be the number of leading hydrogen. So for example, if I had HCl, because I only have one H, my Na would be equal to 1. If I had phosphoric acid, H3PO4, then my Na would be equal to 3, because I have 3 hydrogen here. And then my Nb is going to be the number of moles of hydroxide. So if I have NaOH, sodium hydroxide, then my Nb would be equal to 1, because I only have 1 hydroxide. If I have MgOH2, my magnesium hydroxide, then my Nb would be equal to 2, because I have 2 hydroxides. All right, so let's look at an example. Like I said, they're pretty easy. I'm going to go up a little bit on this. So it says, suppose you know 20 mils of 0.005 molar potassium hydroxide. That's my hydroxide, so that's my base. Solution is required to reach the equivalence point in the titration of 10 mils of an unknown molarity of hydrochloric acid. So that means Ma is my unknown. What is the molarity of the hydrochloric acid? So if I set this up, I know the strength of my base, so that would be my titrant. That would be in the burette. I don't know the strength of my acid, so my acid is my analyte. It would be in the beaker below, and I would be using phenolphthalein as an indicator because it's a perfect indicator for an strong acid, strong base. So my formula is going to be MaVA Na is equal to MbVbNb. And then we would just start filling them in. Ma is my unknown. That's what I'm trying to find. It says that I have 10 mils of my acid. So 10 point would be my volume. For Na, hydrochloric acid, here's the formula right here. It just has 1 hydrogen, so that's going to be 1. And then I take all my base information. Molarity 0.0050 molar. My volume, 20 mils. Both of them are milliliters, so I'm good. And then here's my formula for my base. I have 2 hydroxides, so my Nb is going to be equal to 2. 1 and 2 are counting numbers, so those do not affect sig figs. Everything else had 2 sig figs. Don't have to worry about those weird rules for pH. Everything else had 2 sig figs. So when I get my answer, it should be 2 sig figs. So I'm going to divide this side by 10 and divide this side by 10. So this cancels, and then over here my units cancels, milliliters. And when I do my math, I'm going to end up with 0.020 molar, because I was trying to find the strength. And that would be the strength of my unknown acid. 2 sig figs. This leading 0 right here does not count as a sig fig. All right. All right, so they're pretty easy, so why don't you stop your video and try to do this next one. And then resume the video when you're ready, and we'll work it through.